Right. Good morning. Good morning. So we are going to start the electrostatic field flux model. Flux model. Flux model. What is a flux model? What is a flux model? Why? Let's take it like this. Model. Model. What is a model? What models you know? I asked what models. Right? Don't tell names of models. Huh? What models? Not names of models. Okay, models, fashion models. What's mean by a model? What's mean by a model? Huh? Fashion models. Okay, fashion model. Why fashion models? Yes, you're whispering something. Nothing. Okay. What fashion models do? Can. Yes, can. Right. Okay. So how do you know when ඒ ඇඳලා ඉන්න එක ලස්සනයි ඒ ලස්සනට ඇඳලා ඉන්න එක නිකන් අපිට පොඩි ඉම්ප්‍රෙෂන් එකක් දෙනවා ඔයා ඇඳමත් එහෙම ඇති කියලා. ඉතින් අපේ ගෑන් ළමයි එහෙම මේවට රැවටෙනවා. ඒගොල්ලෝ හිතනවා මමත් අර වගේ ඉඳි කියලා අරගෙන දාලා බැලුවම ඒක ඊට පස්සේ ඇඳුම් එක්කෙනාට බයිනවා. අනේ ඔන්ලයින් එහෙම පර්චේස් කරලා my god this dress looks so good කියලා අරගන්නවා. අරගෙන දාලා බැලුවම මේ ස්ටෝ එකේ ඔන්ලයින් එකේ තියෙන එක නෙවෙයි නෙවලා තියෙන්නේ. Why? Because why you get disappointed? Because you have no idea about this physics content. Physics content. Physics එකෙන් එක මේක මොකද model එකක් කියලා කියන්නේ. What is a model? Model illustrates a perfect conditions of something. It's an illustration. It's an imaginary scenario, right? Sometimes when you see that model on the road, even you don't recognize. Why? Because it's create the perfect conditions, perfect lighting conditions, perfect body conditions, right? And they maintain, plus something else they do. The stitching is perfectly measured for the model's body measurements. So you look at it and you understand, okay, this is so perfect. දැන් කාලේ නම් බැරි වුණාම ෆොටෝෂොප් උත් කරනවා. Right? But anyway, you try to create a perfect condition. So these perfect conditions give you an idea what the perfect idealized system looks like. Do you understand? Right? So when it comes to the flux model, it is the same. When it comes to flux model, it is the same. Flux model. Now you know that you have learned last week, right? I gave some homework. You have done the homework. I can see when I look at your faces. We have done the homework, right? Yes. Yes. So when you think about this questions we did, we found this electric field intensity, force, but you can't visualize it. It's all in your imagination. Okay, there is a charge, it attracts each other, repel each other, this much of force there. So what we do, we create a model to visualize. Like I said about the fashion models. I remember a small story about the fashion models. Remind me to tell it later. That's an interesting one. Right? So, we try to visualize the field. Do we have a field here? Yes or no? Yes. Can you see this? No. You always understand better when you see it. For that we develop visualizing process, visualizing method, visual illustration of electric field. So that is flux model. That is the flux model. So the flux model start from the basics. Yes, positive charge. So we know that electric field intensity is, this is field generating charge, right? And this is the test charge, right? Field generating charge and the test charge. So here test charge is also plus. So we know that there is a repulsion. We have already drawn the force vector. Now that is you can draw when there is a charge. So then the positive charge, negative. As I have read, the positive charge and negative charge, the terminology introduced by can't remember. Introduced by forgot. Sorry. මතක් වුණාම කියන්න. හරි. Benjamin Franklin brought this idea of positive negative charge, if I'm not mistaken, right? And then the flux idea is brought by Faraday, 1900, 19th century, right? So here, what they said, okay, remove the charge, imagine there is a unit positive charge. And the path of the unit positive charge, they have very complicated definitions later, but yeah, okay. Imaginary path, if you keep a unit positive charge, if you keep a unit positive charge here, where it will go? Like that, not the direction I draw, but yeah, okay. You keep a unit positive charge, imaginary. Is there a charge here? No, 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 imaginary, right? Okay, like that. So this is the fundamental concept. So then later they developed, some features, introduced features, imaginary features. That's what the model is about. Model consists other imaginary facts, like they say, okay, when you're drawing this, you have to draw it away from the positive charge, and it is going somewhere. Most popularly says where it goes till infinity, till infinity. And from the last week lesson, you can tell something else as well. What is it? Other than infinity idea, what else? Where? Null point. So in an advanced version, we say it's going to the null point. Can you guess one more place where it is going to stop? Negative charge. Now, if there is a negative charge here, right? So the idea is that the model is that fundamental model, or the smallest element of the flux model is what? Field line. So field lines are drawn away from the positive charges towards the negative charges, because field line is the path of a unit positive charge. Imaginary unit positive charge. You don't have to keep a unit positive charge, because if you keep a unit positive charge, the positive charge, unit positive charge, will also create its own field, so that there is an interaction, right? So we remove that one for a moment. We imagine if there is a charge, how it will go. Practically you can test this. So that is what we call as what? Tell me. Flux, beginning of the flux model. So flux model will develop to the little bit of a serious extent. Right. To understand the electric field and illustrate on a piece of paper, a technique is developed with set of definitions and observations, that is known as flux model. Elementary concept of flux model is force line or field line, force line, an imaginary line which can draw along the line of the motion of unit positive charge in electric field, known as force line. That's what I said. So there is a positive charge here, right? When there is a positive charge, when we keep an imaginary unit positive charge, so force will be away from each other because it is a repulsion, so that will go towards infinity. So we call this is a field line. This is a field line, right? So properties of electric field lines. Flux model is set of assumptions. Answer kala pani flux model, sorry, because we're having an event today afternoon, so Flux model is a set of assumptions of conventions of behavior of force lines. Force lines are always directed away from positive charge. Directed away from positive charge. Now, when you think of this, when you think of this, very popularly it says electric field line starts from positive charges. Electric field line starts from positive charges. That is the most popular situation. That's not wrong completely in detail, but in our A levels, we little bit concern the other sides as well. For an example, so this negative charge, I mean, this is not very good diagram at the moment. I will make it more perfect later because I'm developing this slowly, right? Don't hold it from the tail because this is the end, this is the tail of the story, because I'm developing these lines to explain you what is happening here. So for an example, now when you look at this field line, where did it start? Where did it start? Where this will end? Where this will end? Hmm? Either null point or negative charge or infinity. So that is the broad perspective. That's a broader perspective because we can't say electric field lines start from positive charge in at negative charge. That is, yes, one scenario. So this field line started from? This field line started from? Uh-uh. Either from a positive charge, either from a positive charge or what? Positive charge or infinity or null point. Right? That is the broader idea, okay? Popular one, start from positive charge, end at negative charge. So I have rephrased the content in the textbook. What? It is always away from the positive charge or towards a negative charge. So that line is perfectly all right, but I did not use the word starts or ends. Towards or away. So that is a better word phrasing, right? Right? Okay, positive charge, two positive charges. It keeps drawing. Right. Negative charges, it's always towards. Is that clear? Right. Nice. Force lines can be started either from positive charge or infinity or a null point. Field lines can be ended up at a negative charge, at an infinity, or at a null point. The number of lines that originate from the charge is directly proportional to the magnitude of the charge. This is kind of, little bit of interesting point, and we'll come to that point after you go through the note. Now open the flux model 6.2, the textbook, and go through it, and we'll start discussing the other points. Okay. So number of lines. Now these are like two conventions. I will talk about all these conventions today because that is what we call as the flux model and Gauss law. Gauss has an idea, but to be safe, I have added a line. The popular concept is flux or the number of field lines proportional to the charge, because it depends on the charge. When the charge is bigger, the field is stronger. Charge is bigger, the field is stronger. Right? And to imply that idea, we say flux is proportional to charge. That is the point. But in the history, which is out of the syllabus, but history, there were conventions. These are conventions because no one can see the flux. You can't see the field line. We draw the field line. So you have to decide how do you draw the field line. How do you draw the field line? You understand? My point is, when you draw the field line, you control the number of field lines based on features. There was a convention, the field lines equal to the charge. And there was another convention, field line proportional to the charge, and that is what we call the Gauss law idea. So we'll come to the Gauss law and learn that. Till that we continue the other. Field lines are continuous and conserved. Now get the 2 points. Continuous, you can't break them. You never draw dotted lines, right? We never draw dotted lines. It's continuously going from one of the places we mention. What are the places we mention? Start from a positive charge, go away from positive charge until it meet either negative charge O, null point O, and infinity. No breakages. Okay. And 2, conserved. What is meant by conserved? Conserved. You can't create or destroy field lines. Field is a conserved property. Right? So you can interact with the field, but you can't destroy, you can't create. Now, one charge there, positive charge, that positive charge field is controlled by the charge itself. So you can't destroy the field lines. And there are some complications and mismatchments of the theories. We'll see later. While keeping all these mismatchments, we are learning them, right? The direction of the force line is always tangent to the direction of the electric field at the point. Right? So for that, I'm going to do this interesting part. Field lines, strength directly proportional to intensity lines. Yes, okay. Electric field line do not intercept. I like to start from here. Now, that's why I kept this diagram as it is. Now you understand why I kept this one. So for an example, now this field line, this particular field line and this particular field line, you can see what happened. They try to intercept. But conceptually, and this is impossible, isn't it? Why? How do we define the field line? Field line is an imaginary line when you keep a unit positive charge here, the motion of the positive charge. Okay? Movement of the positive charge. Now, can this positive charge go to 2 directions? Positive charge comes to the point. Positive charge comes to the point and break into 2 pieces and go. Is it possible? Not possible. Right? So it should go to one side. Which side it will go? Hmm? Hmm? Which side it goes? To the direction of the resultant of the force. The resultant force will be only one side. Okay, now you need to figure this out slowly. So, how come this? Sorry, I have drawn the lines wrong. Okay, wait. Here, this is outwards. Sorry about the mistake. So, this is this direction. That is not that side, yes. Because this is a negative charge. Now you understand, okay, the point is this way. Right? Now that will be illustrated in the other diagram. So here it is the same story. When this is going like that, the field line, it goes to this side. So we try to keep this horizontal. So portion. All right. Now you can see at this point it is going somewhere. There are no line like this. That's why I kept it. Because we figured the direction is tangent to the fold. So similarly, this is the tangent part. So lines are tangent. I mean, we can develop this idea throughout. At the beginning, I said, don't rush the idea. Take your time and figure this. You know that. So maybe this line, the line. In between, there is another line. There may be another line. Right? So this is positive charges. So if you draw another line here, so we draw like this, out, lines like this. Keep the directions right always, because I always forget the left hand side one is negative. Yes, it is. This is positive, right? Perfectly all right. Okay. So when you have a positive charge, you will see the same scenario. We'll see a perfect diagrams illustrated in the slides, on the slides. Yes. Here it is. Now here we have seen the shape of this positive and negative charges, what we have drawn. This is a positive repelling idea, right? We are planning to draw them. So unequal charges, how they behave. So these are printed and given. I will explain why. Assumptions of the flux model. Flux model is a set of assumptions of conventions. We have given electric and magnetic field can be represented as field lines which are continuous and stretched across the space. Field lines density reflect the strength of the field at any point in the space. So let me take you through these lines. Symmetrically drawn, right? There are two conventions limiting the field line. First convention, number of field lines are proportional to the charge. Number of field lines are proportional to the charge. So there is a one Coulomb charge, 4 lines. That's I selected, okay? I selected to draw 4 lines. So that is what I select. And what does it mean? 2 coulombs, we have to draw how many lines? 8 lines, not 8 lines drawn here. Right? So this should be 12 lines. That's the reason. So you have to draw the 8 lines, 12 lines in the notebook, workbook. Okay? So that's the idea. Second convention is the Gauss law. Gauss said something bit complicated. We'll come to Gauss law after you read the notes up to that point. Now, Gauss law. Let's do the Gauss law part. The Gauss. Right? Gauss. What Gauss said, actually I will tell you, Gauss law is more useful not for an individual charges. It is very useful for charge distributions. Now the previous theory is okay for individual charges, right? Now for an example, we have charge Q1, Q2, Q3, Q4. And there are charges here and there. Q5. Now how do you figure out the field from this? Now that is not very useful to have individual process. Now, can you draw the field lines like that? No, it is not easy to draw the field lines. So without drawing the field lines, how do we quantify the number of field lines? That is what we call as the Gauss law. Now Gauss said, okay, draw an imaginary boundary, very complicated. Nowadays it's very simple with 3D modeling with the computers, right? When the theory was introduced, it is not that easy. It is just a hypothetical scenario. Sometimes we did not draw the Gaussian surface to understand it, but we are imagining Gaussian surface. What is this surface? What is this surface? Gaussian surface. Why it is Gaussian surface? Gauss drew it. It is surface. So, whatever the charge inside the Gaussian surface, we call Q net. Q net. What is Q net? Net charge. How do you get the net charge? Sigma. All the charges add from 1 to n, right? Take the total charge. When you put the sigma value, when you put this sigma there, there's another story behind it. Close the book. Another story behind this. What is it? You need to add them by considering plus minus sign. Plus minus sign. Or in other words, we can say what? Q1 plus minus Q2 plus Q3 minus Q4 plus Q5, so on. As always, so for math students, for bio students, you don't have to worry about sigma. People who know really good mathematics, you can go for integrations also if you want. Right? Sigma, just addition, summation, right? So when you do this, Gauss said the flux number of field lines is given by what? Q net over epsilon or epsilon. This is a medium property. This is a medium property. Right? This is the charge. Now, what is the difference between the basic convention and this one? Gauss talked about the medium also. That is true, because electric field intensity depends on the charge as well as the medium. Now, in this case, flux is given by what? The net charge over electric field intensity. Sorry, net charge over permittivity. That is giving you the idea of electric field intensity. Electric field intensity measures the strength of the field. So flux is also about that. Idea was clear. I repeat the idea. Gauss law, number one, Gauss law is more useful for what? Charge distribution. When we have lot of charges, if it is an individual charge, use the equation E equals 1 over 4 pi epsilon Q over R squared. So you get the electric field intensity. But we are developing a model because there are a lot of charges or charge distribution, a body of charge distribution. So we have to have a way to find the electric field intensity closer to that point to put the foundation for that. So we introduced this idea, flux Q net over epsilon. Flux depends on the charge, the size of the charge, and the medium property. Clearly, medium property, you know that epsilon goes up, more dielectric, flux is less. In vacuum, epsilon naught, the most number of field lines or the flux associated with it. Okay? So now here you can see charge over epsilon, and flux is again a scalar because you are using two scalars here. Flux is also scalar but with a plus minus sign. When the net charge is positive, flux is positive. Net charge is negative, flux is negative. Is that clear? And my next question for you, So what is mean by positive flux? What is mean by negative flux? What is mean by positive flux? What is mean by negative flux? What's the meaning of it? Sorry? Yeah, I understand that. But that is about the net flux, net charge you are talking about. Charge is negative, so this is negative flux. Net charge is positive, more negative charge, I agree with that. More net charge is negative means more negative charges than more positive charges. But when it comes to field lines, what is mean by field lines positive, field lines negative? We have already learned you have to map that. I didn't get it. Repeat. Positive. Flux, I'm asking flux. Very good. When this is positive means the effective number of field lines are outwards. Effective. Effective. Why effective? Because negative charges bringing field lines inwards, positive charges sending field lines outwards, negative charges bringing field lines inwards, positive charges sending field lines outwards, positive charges sending field lines outwards, but end of the day, the total net charge is positive. What does it mean? Inward, outwards, everything, you add up them to a crunch of field lines. The final output of the field line is outwards. If the net flux is negative, this is negative, what does it mean? effectively the final count of the field lines are towards. Simple. So this is the basic idea of the Gauss law. Right? Okay, turn to the note and go through it. So, key points: Gaussian surface is an imaginary surface which we can draw by connecting all equipotential points. Interesting. We'll see what are the equipotential points. Number of field lines limited by the Gaussian surface is known as flux. Yes, right. Flux can be positive, negative, or zero. When the effective flux is zero, there is no net charge inside the Gaussian surface. In other words, number of field lines crossing the Gaussian surface inwards is equal to the outwards. So now flux phi can be 0, positive or negative. So all three scenarios there. So that is this one here. Mathematically you can see Q net equals 0. So therefore flux is equal to 0. So when the effective flux is positive, the net charge inside the Gaussian surface is positive. In other words, the number of field lines coming out of the Gaussian surface is more than the number of field lines going into the surface. Right. Okay, yes. So net charge is positive, so you get flux is positive, that is flux is outwards from the surface. When the effective flux is negative, net charge inside the Gaussian surface is negative. In other words, number of field lines going to the Gaussian surface is more than the number of field lines coming out of the surface. So Q net is less than 0. So that is negative, negative over epsilon. External charges do not contribute for the flux through the Gaussian surface. Now, I like to explain this slightly more by visualizing the idea. Right? Now, external charges, say for an example, there is a charge plus Q outside the Gaussian surface. Plus Q outside. I'll use a color, wait. I'll use a color you to see that it's an external one. Say plus Q outside. Now say this is sending a field line, okay. One goes inwards. So will it increase the flux or decrease the flux? No, why? No, nothing, why? This is going outside. Whatever comes in will go out. That's why this closed imaginary surface is important. You got this? That is the concept. Outside charges from outside the Gaussian surface will not affect what? The flux inside the Gaussian surface. So yeah, flux density, the new part. It's a derivation of flux model. Flux density. Flux density. I keep the keywords on the board. Flux density. Flux density. Density idea, you know that. You need to divide it by either by density idea. Either volume or area. So in this case, it is area. Density. So flux divide by area. So generally we call perpendicular flux. That is called flux density. Flux density is a vector. Flux density is a vector. In other words, it is a perpendicular direction. Can you remember? I don't know whether I did it here with you all or 2027s. Now there is a field line. There is a surface. There is a field line and there is a surface. Right? So now you know that, sorry, it is going through, okay, we'll draw it little bit of easy format. Right, okay, this is easy, okay, you to understand. I'm thinking about a format. Now this is a flux, which is creating a theta degree angle. Perpendicular component is always what? Sine theta, whatever it is. And this component is cos theta. You know the cos product and the dot product. Maths people, cos product and the dot product. Cos product is the මතකද නැද්ද? Maths people vectors ඉගෙන ගත්තා කියන්න. බයෝ අයට ඕනේ නැහැ ටික. Cos product is the dot product or cross product? Cos component product. Is it a cross product or the dot product? Dot product. Perpendicular component is what? This cross product. Cross product is vector product. Right? The perpendicular component කියලා කියන්නේ always what? The vector product. Bio people, don't think about that much. You can just remember what? Remember that this is a vector. So on the other hand, B dot A is what? A dot product. And that's why this is a scalar. Okay? This is a dot product. This is coming from the cross product idea. Okay, is that clear? Right, okay. Enough. Bio people are frowning at me, okay. So we'll go for the note. Flux density perpendicular. Thank you. Electric flux perpendicular to unit surface area is defined as flux. So flux over area is flux density. Now flux is Newton square meter per coulomb. So you can take the unit of flux from here, unit of flux, right? Unit of charge over unit of what? Epsilon. Charge is coulomb, unit of epsilon is. Help me people. මතක් කළා කියන්න. බරපතල ප්‍රශ්නයක් නේද? මොනවාද? ආවේ coulomb squared, okay, and per meter squared, okay, and per Newton. Right, so one cancels. So Newton, right? Newton per square meter per coulomb, right? Right? Newton, sorry, square meter per coulomb per comes up, yeah. Coulomb per coulomb over square meter. So that is Newton per coulomb. Now when you see this Newton per coulomb, Newton per coulomb, what do you remember? What comes to your mind? Force නෙමෙයි. Electric field intensity. Homework කළා ළමයා. Electric field intensity, Newton per coulomb, force per unit charge. So simple terms, what is capital B now? Electric field intensity. Now match the ends. Electric field intensity is B, then why the hell we have gone around the bush to find electric field intensity here? Simple. That is for the charge distribution. Can we use Q over 4 pi epsilon Q R squared? No, we can't, because it's only for individual charge. Now this is more useful because we don't have point charges all around. If it is a proton or electron or nuclei, So you can use Coulomb's law. But this is charged. For an example, can we use QO 4 pi epsilon r squared? No, because this is a different shape object. So to find the electric field around the vicinity of this one, we need what? Gauss law. That is the most useful theory to find electric field intensity. So that's why we are coming to the applications. We are going to do simple applications now and some complicated ones later. Go through the note up to this point. Right. Okay. Question එකක් ඇහුනේ අතන. Sorry, question? No question. You want to go to hunger concert? Something else. Okay, wait, I'll come. I'm working with my students and teachers very closely. That is in a way good thing. Why? I don't miss events. I anyhow try to go. Last year I went for 6 weddings. මතකද දන්නේ ඔයගලන්ට? 6 weddings on 3 days. ඒ කියන්නේ එක දවසේ වෙඩිත් දෙකයි. ඒතර ඒකෙන් 4ක්ම මැරි කරපු 8 දෙනාම ස්ටුඩන්ට්ස්ලා. ඇයි බම්බර ගණන් බැරිද? හරි දාන්න එපා. ලයිව් නෑ නේද? ලයිව් තියනවලු යන්න. ඉතුරුට. ඉතින් ඒ වගේ තියනවා ඉතින් පොඩි පොඩි වෙලාවලට. එතකොට යන්නේ කොහොමද වෙඩින් එකට? කවන්නේ තියන්නේ එහෙනම් ලයිව්. නැත්තම් applications of Gauss law කියලා ළමයි ඒවා ලියාගනි. application of Gauss law කියලා මේ ටික ලියාගත්තාම මාර ප්‍රොබ්ලම් යන්නේ. ඒක වෙලා තියෙන දැන් එතකොට යනවා පූර්ව සෙරමනි එක තියෙනවා සමහර අයගේ. එතකොට එකකට පෝරුව සෙරමනි එකට යනවා. උදේ තිබිච්ච වෙඩින්ස් තර්ස්ඩේස් දෙකක් මං හිතන්නේ කට් වුණා මට. උදේ යනවා 9:30 10 වෙනකොට යනවා. ඊට පස්සේ කොහොම හරි 11:30 වලට පෝරුව වැඩි කරලා එහෙන් කන්නේ නැතුව අනිත් එකට යනවා කන්න. right ඊට පස්සේ රැටත් එහෙමයි සමහර ඒවාට ගිහිල්ලා decide කරනවා which place I'm going to have my dinner. But I'm attending anyhow. Because that's why they invite me, right? I mean, they're expecting me to be there. So that's how things, it's a little bit tiring and tough, but try my best to go to everything. Because we don't get like 2 chances sometimes. That's why I said like, randomly I had that meta problem to be solved. So that's why I went there. So very next day it happened, like it's like that. Okay, so we'll go back to our work applications of Gauss law. Abhi gamu lazy maker. So we'll take the easiest one to figure this out first. Okay, it's the easiest one. Flux density O, electric field intensity at a point r distance away from a point charge q. Right. So we have to create a Gaussian surface. So what is the Gaussian surface we try to develop? What is the Gaussian surface we try to get here? Sorry? Circle, yeah. Sphere. Circle. Sphere, right? Yeah, we draw a circle. That's why I asked that question separately, because we draw a circle because we can't draw three dimensions on a book, on a paper. So you need to remember this is a spherical surface because field lines must be perpendicular. We'll learn why it should be perpendicular at the middle. Yeah. So when the lines are going this way, so when it is perpendicular, now what is the combination of the Gauss theory? Number 1, we select point P on the Gaussian surface to find the electric field intensity at the point P. But I told you clearly, you don't want to use the Gauss law for this example. Why? Because this is a single charge. Gauss law is more useful for charge distribution. Why I am doing this then? You to understand the Gauss law, right? We take the easiest format first. The distance is simple r, Gaussian surface 4 pi r squared. Gauss law says phi equals q over epsilon. Phi equals q over epsilon. But flux density definition says it is flux over area. It says flux over area. Okay. Flux over area. Now what is the area of the Gaussian surface? 4 pi r squared. So you put 4 pi r squared connecting these two. Now what you will get here? What comes to your mind again? B is E. B is E. B is the flux density at point P. But when you derive that one, what you got the exact expression for E. Right. So we finalize this, conclude this B equals E. But you need to do this derivation throughout. In exams, most of the time, they expect you to go through the full process to get the final digits. Is this clear? Right. And go through this one because probably we can go for a break if it is clearly done. Because after that we can rush through the other applications, because this is the key to understand. Yes, we can go for a break after this. So after the break session, yes, electric field intensity at the vicinity of a charge conducting sphere. So here it is. There are three cases. Case 1, r smaller than a, r equals to a, r greater than a, where a is the radius of sphere and r is the distance to the point from the center of sphere. Something wrong with the animation. Laptop is playing crazy. You can't see a sphere here, right? මට අර ඊයේ රෑ ගැන පොඩ්ඩක් බය හිතුණා මට පේන්නේ නැතුව තියෙනවද දන්නේ නැහැ මේකේ තියෙනවා මේකේ නැහැ. ඇනිමේෂන් එක ලැප්ටොප් එකේ තියෙනවා මේකේ නැහැ. නෑ ෆ්‍රීස් කරලා නෑ. දැන් මාරු කරානේ මම. නෑ වලී තියෙන එකක්. That magic. Ghost. Siochem ghosts. Why? Presentation cable is removed, but still presentation running. Freeze එකකුත් නෙමෙයි තියෙන ප්‍රශ්නේ. Right. That's better. Come better. Right, we'll go ahead again and restart. That's the best thing. Is needed. That's why. I don't like to go to the wood. Yes. PowerPoint. Sorry, the projector is going to burst. Boom. It's making the sound, weird sound. Okay, we'll see. I think it's overheated. Projector may be overheated still. මේක හරියන්නේ නැහැ නේ. Okay, finally. Right, let's see. Let's see how it goes. Unfortunately, I think we are in a big technical problem. Okay, right. Yes. Okay, finally, the sphere displays. Right, so now electric field intensity at the vicinity of the charge conducting sphere, this is one. and R equals A, R less than A, R greater than A, first of all, we provide some charges to this sphere. So we give some charges to the sphere. So what are they? Hypothetically think that we give the charges to the center. Charges to the center. Inject charges into the center. Solid sphere. Okay? Solid sphere. So when the charges are there in the sphere, right? Now what happened to these positive charges? What will happen to these positive charges? Sorry? Sorry? Repel. Very good. Repelled. Simple. And they repel and go to the, go where? Go to the surface. Why it is not going away from the surface? Why it is not going away from the surface? Why it is not going away from the surface? Huh? Sorry? Because of the field. Why it's not going away further? Why is that is becoming the boundary? ඌනේ මේනේ අහන්නේ මට උත්තර දෙනවා. ඔටි කන්න නැතු මෙතන. Null point, no. Keep answering, very good. I got good answers. Talk. No. Why it is not moving away from this point? When I give the answer, you feel like how dumb you people are. Why these charges are not moving away? Where are the negative charges? No negative charges. These are the all excess charges, positive charges. Why it is the maximum distance? How do you know it is the maximum distance? Yeah, it must be at infinity. This is not infinity. Huh? Ko bitya? Bad. This is the conducting part. This is not the conducting part. Charges to travel, you need a conducting medium. So this outside the solid metallic sphere, the outside environment is not conducting environment. When it is not a conducting environment, what happens? It is not moving out of that. So the repulsion is still there, but it's not moving out. So we are looking at a point inside. We are looking at a point inside. This is point P, r distance away from the center. R distance away from the center, right? R is smaller than A. Now this purple color dotted line indicate the Gaussian surface. The Gaussian surface. So this Gaussian surface, what is the total charge inside the Gaussian surface. What is the total charge inside the Gaussian surface? What is the total charge inside the Gaussian surface? 0. Very good. So net charge is 0. So therefore flux is 0. Since flux is 0, flux density is also 0. Flux density is 0. Electric field intensity at the center of, at the middle of a solid conducting sphere is 0. Okay. Is that clear? Right. The next one. I select a point just outside R equals A. R equals A point. Point X is a point on the solid sphere. On the solid sphere. Now tell me, when you think about the solid sphere, what is the total charge inside the solid sphere? What is the charge inside the solid sphere? Now there is a solid sphere, right? Okay. The solid sphere. Now what is the charge inside this Gaussian surface? I draw the Gaussian surface just above the surface. Yes. Huh? 0? Plus Q? Okay. Plus Q. Yes, very good. It is plus Q. Then what diagram එක බැලුවොත්? Diagram එක බැලුවොත්, yes. නිකන් ඔයාලට පේනවා නිකන් මේ charges තියෙන එළියෙන් වගේ. That is not true. Go to the atomic level and try to figure this out. So there is an atom. We enlarge it to billions, trillions of size. This is the atom. Say this is a sodium surface. So this is the atom. And what is this? This is the nucleus. Now what exactly mean by a positive charge? What exactly mean by a positive charge? What is exactly mean by a positive charge? Sorry? Removing an electron. Okay, correct, very good. So we have removed the electron out of the final orbit. Now the final orbit is here. We remove this electron out. Where the positive charge is now? At the nucleus. Excess proton. What is a positive charge? A proton. What is the positive charge? Excess proton or deficiency of an electron, a cation. So, here this is the positive charge. So, this is the surface. Surface. No electron there. No electron there. No electron there. So now you understand this is my Gaussian surface as well. So the positive charge inside the Gaussian source, outside the Gaussian source. Right. Go to the diagram and you understand. Now we have drawn it outside because we are drawing a positive sign. Sign doesn't mean that is a charge. Sign is outside, but the charge is inside the surface. Atomic level understanding. You understand? So therefore, the charge inside the new Gaussian surface is also capital Q plus capital Q. Plus capital Q. Q naught is plus capital Q. And flux densities, B equals phi over A. Phi is Q over epsilon. What we get? B equals 1 over 4 pi epsilon. 1 over 4 pi epsilon Q over A squared by A is not a variable. A is the radius. A is the radius. A is not a variable. A is not a variable. A is a constant. That is the radius of the sphere. R is the variable. Now in this case R equals what? A. So this is a fixed value. So B equals E. So you can say electric field intensity equals Q over 4 pi epsilon R. You can replace R by A squared. Is that clear? Right. Now we go to the next one. Third case, R bigger than A. When R bigger than A, the new point is Z. So we get the Gaussian surface. It's easy. Now what is the total charge inside the Gaussian surface? That is plus capital Q. Plus capital Q. When you consider plus capital Q as the total net charge inside the Gaussian surface, we can write the flux as Q over epsilon, flux density as phi over A, phi is Q over epsilon, A is 4 pi R squared. This is R is not a constant, this R is a variable because it can be, it is whatever bigger than simple A. So it's a variable. So remember, electric field intensity is Q over 4 pi epsilon R squared. That R is a variable which is bigger than simple A. So we can base these things and draw the variation also nicely. Now I'm going to explain. Whatever, when R is to the right, to the positive direction up to A, the sphere is there. Inside the sphere, what is the electric field intensity? 0. So you draw the 0 value here, right? 0 here. And at the surface, we know the figure there. What is it? Q over 4 pi epsilon A squared. That A squared is a value. And from that point onward, it is 1 Q over 4 pi epsilon R squared. So this is varying as 1 over R squared. That is inverse proportionality square. Square of the inverse. Right? Square of the inverse. So that is what we call as hyperbola. So hyperbolic curve. Right? Hyperbolic curve. So the variation of electric field intensity is 0 at the center, goes to the maximum at the surface, Q over 4 pi epsilon A squared. After that, it is reducing inverse proportionality to the distance. Square inverse proportional to the distance. And why we have negative and positive sides? Because electric field intensity is a vector, and to the right you consider as positive, to the left you consider as negative. Is that clear? Right. Open the book, go through it line by line, because you have to do it alone by yourself one more time. So remember to study and finish, because this lesson is easy as well as very difficult. Why this is easy? When you study this, you remember, you practice, and the same thing coming. Okay? But why it is difficult? There are so many applications you need to remember. Right? Right? Take your exercise book, close your textbook. Close your textbooks. And now you're gonna do something special. Now your first exercise. Keep eye on this. Charge density. Very simple. The total charge Q. Charge density, I told you, either dividing by area or dividing by volume. In this case, charge density divide by volume. So capital Q amount of charge is distributed throughout a sphere. For an example, charge volume is V and Q over V is what? Charge density. Charge density. I use the same notation of density. What? Rho. Rho equals Q over V. Q over V. So the unit is Coulomb per cubic meter. Just keep it in your mind. Rho equals Q over V. Rho equals Q over V. Is that right? Is that clear? Right. Okay. Now, based on that, charge density can be extended. Volume of a sphere is 4 over 3 pi a cube. So we go further and get the Gaussian surface idea. Right? Gaussian surface idea. Charge inside the Gaussian surface. Say R smaller than A. Sorry, R smaller than A. So the Gaussian surface is inside this. So when the Gaussian surface is inside this, we can get the total charge inside the Gaussian surface as Q divide by A to the power 3 into R to the power 3. Slowly look at it and try to understand. Ask any questions you want to ask, because this is a solid insulating sphere with a uniform charge distribution. Solid insulating sphere with uniform charge distribution. For the entire sphere, the total charge Q over total volume is density. So when you think of a Gaussian surface, when you think of a Gaussian surface inside this, now you can see there is an arrowhead, but the surface is not there. So assume a surface like this. Now the point is not outside, point is inside. Right? You got this? So now when you look at a Gaussian surface, this is the Gaussian surface, the charge inside the Gaussian surface, simple Qg, charge inside the Gaussian surface. So the volume is this volume, that is 4 by 3 pi r cube. 4 by 3 pi r cube. So you know that same density we are talking about. So we equalize, we get Q value in terms of capital Q r to the power 3 over a to the power 3, right? So now we can go for the question. Now keep these points in your mind, right? Qg, capital Q over r cube over a to the power 3. Okay, that is the value you need to remember. I will keep it here. I'll keep it here, okay? Now what is Qg? Capital Q r to the power 3 over a to the power 3. Okay, right. Now this is your turn. You need to do this question alone. You have only one reference, that is the point charge reference, right? Sorry, or the conducting sphere reference. Continue. I'm coming to check one by one. These are the questions coming in exams. Okay. Yes. So we'll see what is wrong with this. සමහරවිට process එක මතක නැහැ. ඒක තමයි පාඩම් කරන්න කිව්වේ. process එක පාඩම් කරගන්න ඕනේ ඊළඟ එකට යන්නත් ඉස්සෙල්ලා. දැන් මේක තමයි දවසෙන් වැඩේ. So we have a solid sphere, insulating sphere. So the charges are distributed all over. Charges are distributed all over. So R less than A, Gauss law. Phi equals Gauss law, Gaussian surface Q. Charge inside the Gaussian surface is QG over epsilon. So QR squared over A, sorry, QR cube over A cube. That is coming from the density definition. Very good. And we have this flux density is phi over area. Area is 4 over 3 pi r squared. Sorry, 4 pi r squared. 4 pi r squared. 4 pi r squared. 4 pi r squared. R squared cancelled. Now what we get? Q over 4 pi epsilon A cube into R. Wait. That's one format of explaining this. One format of presenting this. Q over 4 pi epsilon A cube is a constant. Q is the total charge inside the sphere. 4 is a constant, pi is a constant, epsilon is a constant, A is a constant, so A to the power 3 is a constant. So B constant into R, so that is linear variation. Y equals mx type. Do you understand that? Is this clear? Do you understand? Understood? Yes? Okay. Check whether you got this. People who got these answers, write good numbers. Only 1, 2 people, 3 people couldn't get it. Okay. And you don't have to copy down, but you quickly adjust your answers. The reason you don't have to copy this down because this is there printed. This is there printed in your notes. So that's why you're doing it the exercise wise. So that's why I don't like the printed notes. Why? You try to by heart this. Now you have to understand and do it. Right? So that's, I have changed the techniques. I have changed the techniques because now with the trend, with the improvement of the processes, what we do? We do slides, we do notes, but we don't completely skip the works on the board and we don't skip your working on the exercise book. So what we supposed to do? Keep the textbook away, redo the work here. You don't have to copy down the notes. Copy down the notes part is there in the textbook, printed textbooks. So you need to figure this out. These questions, these are examples. Sometimes these are models for standard shapes of objects with the charged bodies. So we use them. We use them to practice the Gaussian law, right? Okay. Right. The next one, R equals another format, Q equals 4 over 3 pi A cube. So I put it here. And some people had taken this one. So 4 cancelled, pi cancels, A3 cancels. So now electric field intensity is given. Electric field intensity is given in terms of charge density. Charge density. Okay, right. So now we select the object on the surface. Sorry, Gaussian surface is the surface of the sphere. So now you know that QG equals Q because the total charge. So when you know that QG equals Q, Q is sigma into 4 over 3 pi r cube Flux density is flux over area. Area is 4 pi r squared. R is A in this case because this is the radius of the sphere. 4, 4 cancel, pi, pi cancel, A3 cancel with A2. Now we get the idea. Rho A over 3 epsilon. It's the same equation. Same equation. Only difference is R replaced by A because A is a constant, R is a variable. Do you understand this? A is a constant, R is a variable. So you replace R by A. This is a fixed value. Okay, right. R bigger than A. We repeat the same process. Qg equals Q. But flux density idea is slightly different. Q over 4 pi epsilon R squared. But if you want, you can replace Q in terms of what? Density. So density into, charge density into 4 over 3 pi A cube. So cancel, cancel. Equation is a bit complicated. You can see the format. But anyway, rho, charge density is a constant. A is a constant. Epsilon is a constant. 1 over r squared. R is variable again. So that is a inverse square law. Inverse square law means what? Tell me, inverse square law is what? Hyperbola. The shape is a hyperbola. Okay, right. Now what you're supposed to do, go to the note, textbook, only go through this example too. Go through it again and again. People who couldn't get the previous, by yourself. So please go through the textbook and study, understand, and keep it ready for the next question. variation of electric field intensity of charge insulating sphere. Now, at the center, inside the sphere, how does it work? Huh? Linear, very good. So that's a linear variation. After that, hyperbolic variation. Now close the textbooks again. Right? And the peak value, you know that, rho A over 3 epsilon. Right? That's a peak value. Inside this, rho R over 3 epsilon. The other side, rho A over 3 epsilon into 1 over R squared. Is that clear? Right. So we are going to the third application. You people are going to do this by yourself. Surface charge density. Now, first one, charge density. Flux density. Third density you are learning, surface charge density. Density is always about dividing by area O. Close. Right, okay, fine. Amount of charge per unit surface area is called as surface charge density. So charge amount Q, surface area A, Q over area E is what? Density. Is that right? Is that right? So the unit is coulomb per square meter, coulomb per square meter, right? Keep it in your mind, okay? Keep it in your mind. And we are going to deal with this. Now what is example 4? There is a thick large, no end, conducting plate. I'll give you the suggested Gaussian surface. Now all charges are outside the plate. Now you know the reason. We learnt it in the conducting sphere example. Can you remember? Yes or no? Yeah, okay. So here the positive charges, outer surfaces, right? Why no charges inside the surface? Why no charges inside the surface? Conducting plates cannot hold the charges inside because it's repel and come to the surface, right? So this is my Gaussian surface opinion. Small circular Gaussian surface with a cylindrical shape, and you don't have to make this circular. This can be any weird shape, but this is a kind of a tube. Cross section can be anything. And this tube, part is inside, the part is outside. So that's all I can tell you. And give a try to get the electric field intensity at the point outside the surface. Okay, right. Give a try. Start. Right. Electric field strength at a point closer to a charged, infinitely large, thick conducting plate. Thick conducting plate. So we have outside and inside. So area I like to call AO delta A. Area I like to call AO delta A. Right? So the surface charge density, be careful. Surface charge density is sigma. So charge inside this is sigma into delta A. Sigma into delta A. Now we can write the charge sigma into delta A. If it is the total solid sphere, sigma rho into volume. Now this is area, surface area, sigma into delta A. So then what do? We multiply, we divide this by epsilon to get the flux value. Right? Flux value. Q net over epsilon, the flux value. Flux value, right? Flux into density. So now we know that flux density is, this is divided by area. What is the area again? Delta A. We'll multiply delta A cancelled, and flux density is sigma over epsilon. Sigma over epsilon. Is this clear, right? So we know that electric field intensity at point X is sigma over epsilon. People who got this answer. Right. 1, 2, 3, 4, 5, 6. 6 people couldn't get it. Yes. You can go through it one more time. Yes. The graph wise it is easy. Graph wise it is easy. No field, the constant field. And go through the note, and open the textbook and go through it completely. Please go through it completely. Hurry up. Hurry up. People, study and finish. Hurry up. Hurry up. Study and finish. Okay? Any questions? Because we are going for the lunch break on time. Any questions? Any questions? Questions? Right. After the break, our plans to continue this part. There are a few more applications we are going to discuss, and we are going to understand electric field intensity and potential gradient relationship. So that is the last part of this flux and 6.2, right? So what is the remaining component? That is capacitors. Usually we do the capacitor part after doing little bit of current electricity. Reason, capacitors are connected to the electric circuits. So without knowing the circuit behaviors, you can't understand what capacitors. Honestly, you can understand the capacitors, but applications, questions cannot be done without current electricity components. So we'll meet after the break, lunch break.